Hi, we should get started. We're very happy to have Randall Lewis here today, who is Chief Research Scientist in the Knowledge Group at Google. I want to be in the Knowledge Group. Probably fit better in the Obfuscation Group. Before that, he was at Yahoo Research until last May. And before that, he was a PhD in econ at MIT. And we're very happy to have him.
Thank you. Okay, so the paper today I'm going to be presenting is perhaps a little strange. Both my presentation is going to be a little bit non-standard, and maybe the content will be a little bit non-standard. But I don't want that to keep you from interrupting and asking questions as we go through. And so just to warn you, there are 250 slides, but don't worry, I'm going to get through them all. So the title of the paper is On the Near-Impossibility of Measuring the Returns to Advertising. This is joint work with Justin Rao, who's at Microsoft Research. He's a former colleague of mine at Yahoo. And the disclaimer, as you can see it, is these are my own opinion and Justin's. So, okay, so just give you a bit of an introduction about advertising. Advertising is a $200 billion a year industry. That's roughly 1.5% to 2% of GDP, or about $500 per person per year. So if you think about it, that's a pretty good amount of money. It's supporting many free services that constitute the majority of Americans' leisure time. For example, leisure time is spent divided, more than half of which is watching TV. We spend some time on Facebook and Google Plus, of course, and maybe Hotmail and other things, but you know. And then there's a variety of other activities we engage in. If you think about each of these categories, there's a significant component of them that are actually monetized. So a very large share of our free time is actually monetized, in part through advertising. Yet the effects of advertising are poorly understood. And so that's kind of the assertion that we're making in this paper. Get that mouse out of the way. So just to give you an example, we have a billboard here of Coca-Cola. Just to give you a sense of the magnitudes of money that are being spent, a billboard like that is about $100,000 a month. NASCAR sponsorship is roughly $25 million a year. Just to get your name, DeWalt's name on that car. The Minute Maid Park, we're talking about $3 to $5 million per year for a park naming sponsorship. So television, we're going to refer to the phrase CPM occasionally. That means cost per mil or cost per thousand. So it's about $10 to $25 on TV to get 1,000 views of a commercial, or 1,000 people to view your commercial. Online, it's about $1 to $8 for a similar effect. For that display ad there on the right, it's capital One. But the real question is, how expensive is it to fly a plane with a banner? And you know, we have no idea how much that costs. But this is just another form of outdoor advertising that, if you think about it, it's going to be really hard to determine the impact of these ads. How do we know how many people saw the Minute Maid Park? How many people saw that flying ad? And so an interesting quote in 1990 by Abraham and Lodish in a seminal paper involving the TV advertising effectiveness research, they say, as their opening statement in their paper, until recently, believing in the influence of advertising and promotion was largely a matter of faith. So just keep in mind that that quote was predated by $4.7 trillion of 20th century advertising spend. That's just an enormous amount of money, and yet that's a whole lot of faith if we're spending that much and we still don't know. So let's just talk about a more current example. So it's 22 years later. Now do we know anything better? Well, in 2012, an amendment last July was proposed to the Armed Services Appropriations Bill that would have eliminated $74 million in annual advertising expenditure at sporting events. Specifically, it would have eliminated the NASCAR sponsorship for all of these various military groups. This amendment was defeated just barely, 216 to 202. So in other words, they still had the right to go and spend that money. However, our reading was that nearly zero evidence was presented for or against the effectiveness of this advertising. In the end, rhetoric dominated. Jack Kingston from Georgia, a member of Congress, said, if someone is going to sign away 6 years of their life, it's going to take more than an ad on an automobile, right? Like, that makes sense. There we've got the Army, the Army NASCAR. However, on the flip side, we have Jeff Burton, a veteran NASCAR driver, doing the standard revealed preference argument. I don't think they're throwing money at it just for the hell of it. They must be doing it because it works. Why would they be spending the money if it wasn't effective, right? Like that's sort of the standard economist statement that, well, revealed preference says that it must work. So tens of millions had been spent, and people were arguing if it had done anything. There was a little bit of research presented, but it basically all degraded down into rhetoric. So it seems kind of strange. The digital measurement era, however, is going to give us two key advances that might help us make this problem a little bit more tractable. In particular, the first advance is that ad delivery and purchase data can be linked at the individual level. We have a display ad for the RAV4, and we have a display ad or an actual purchased RAV4 sitting in somebody's driveway. We can link the person that saw the ad and the fact that they purchased the car. The second advance is that ad delivery can actually be randomized. So we can decide whether the person is going to see the RAV4 ad or they're going to see some unrelated ad like a Red Cross ad. And yes, we do toss, actually, we have a little machine that tosses quarters at Google in order whenever we need to run an experiment. It's a kind of a cool mechanic. No, that's ridiculous. So we address the underlying puzzle here. If so much money is spent, how can economic agents have such imprecise beliefs about the return? So we analyzed 25 digital advertising experiments amounting to $2.8 million that were run at Yahoo. They involve large retailers and financial services firms. You would have known the names of all of these companies if you at all go shopping or pay attention to anything. So these advertisers were running relatively large, fully randomized field experiments, and data sharing agreements gave us the sales and sign-up information, so we could link ad exposure and the outcomes. And in the end, we were able to quantify how difficult it is to measure ad effectiveness. In sort of a quote you should think about is, it's very hard, but it's not impossible with good data to measure that ads actually do something, okay? But something to keep in mind is that most ads cost less than a penny per delivery. So a given ad impression is ridiculously worthless from an absolute economic perspective. And it also, any given ad is going to represent a very small share of the roughly $1.50 per day per person that is being expended. So think about, you get hit by 150 ads today, and how many of those can you even feasibly act upon given the time constraints that you have, even if you were able to pay attention to all of them. So in the end, a small impact can actually generate a really large ROI, because we're not looking for hundreds of dollars of effect per ad, but rather we're looking for pennies in order to offset the cost of those ads. So one observation that we find is that sales for many or most heavily advertised categories are very noisy, and this is what makes experiments underpowered. However, there are bigger problems that lurk for observational methods. So we could potentially just take ad data and we could take sales data and we could put them together and say, people who saw the ads, they purchased more. We might be able to do something like that. However, the big problem here is that ads are not delivered randomly. If they were, then we would have some problems. So let's just consider one example about where this selection bias can cause problems. So suppose that an advertiser gets a marginal profit of $30 per incremental purchase. So think about this as a pair of jeans, sort of an average pair of jeans where the markup's about 50, where the gross margin's about 50%. The ad's going to cost half a cent. This means that it's going to take 1 in 6,000 ads to break even. So it's a very small share. And then suppose that targeted individuals, due to some targeting algorithm that we've been able to develop, is going to discover that the target individuals that we're trying to show the ad to are actually 10% more likely to purchase relative to a very low baseline rate. And so in the end, this means that the selection effect of the difference between the targeted and untargeted population could be 600 times the actual causal effect that is economically interesting that we're looking for. So there's this big disconnect between how much selection bias there might be and the economically interesting effects that we're looking for. So these large selection effects and weak treatment effects are precisely the opposite conditions that observational methods are generally suited for, like the Mincer wage and education regressions and many other common situations that emerge in the social sciences. So we're going to discuss market and industrial organization implications. We're going to address some concerns that you might have about how representative our firms are, and we're also going to talk about maybe some other similar markets and conclude. Okay, so just to calibrate our thinking, we need to think about what is the advertiser's problem. We're going to take an exceedingly simple model of campaign evaluation. So campaign is a common unit in the advertising literature. I'll talk a little bit more in a minute. We're not going to look at full-blown optimization. We're just going to focus on how much to advertise, if at all. So thinking about varying costs. So given a certain expenditure, what is the return on that expenditure? Just think about advertising as an investment. I spend a certain amount of money. I expect to get some sort of return on that investment. So we're going to have a little bit of notation here. It's not very complicated. But we're going to assume that a campaign is in a single media. So this means, let's just say it's TV. And we're going to define it by the cost per person, C. So we can vary how intense we want to advertise. People are going to be identical, and then we're going to think about this sales impact function, which is continuous and concave. If we spend more money, we should expect to get more effect. However, we might expect some of those effects to eventually diminish. And also the gross margin for the particular advertiser, M, is known. Okay, so this gives us our ROI calculation. Pretty trivial. We take the sales impact, multiply it by its margin to get the profit, the net profit, or gross profits, and then we subtract out the cost and divide by the cost. So pretty simple calculation, trivial. So this is what it looks like when we take a look at in a graphical perspective. What is the advertiser's problem? Everybody's seen one of these graphs at some point in their life. We have cost on the horizontal axis, and we have on the vertical axis the gross profit. So the standard first order condition will say we want to set the slope, we want to get the marginal profit equal to the marginal cost. And so this will give us C star. This is where the advertiser should be sitting. They should be spending C star, and they can maximize profits when they're in that setting. If we go a little too far, we might be in negative ROI territory. We might be burning money. We might be just over advertising, or we might be under advertising. Any of those things could be happening. So that's our simple model, but in reality, the world is way more complex than this of advertising. We have things like creative rotation, cross-media, the TV, mobile, print, a whole variety of different interacting effects that we might be worried about. There's targeting, selecting your audience, stochastic or random delivery, and just there's a variety of these other complicating factors. We're just going to ignore them for now. So to motivate the advertising campaign, we're looking at campaigns because it is the fundamental unit of ad effectiveness. It's used widespread throughout the world of advertising, and as an example, a Google Scholar search of advertising campaign yields 49,000 unique documents. So advertising campaigns are kind of the unit of observation, the unit of evaluation in the world of advertising. So this campaign evaluation focus is what we're going to center around. So we have the advertiser's problem, but now let's calibrate it using some data. So we're going to use the 25 display advertising field experiments run at Yahoo, and these were done while we were research scientists there. So the data sharing gives us sales records paired with ad delivery at the individual level. So we have an individual. We have events which are they engaged in a transaction, and we're able to sort of link that over time with the actual individual ad impressions. So the exact time at which the ads were shown and the exact times at which the sales were made. So again, the typical display ad campaign is going to be 1 to 2 cents per day over roughly 2 weeks. So again, we're talking about pennies per day. This will result over the course of a campaign of somewhere between 20 and 150 impressions, depending on pricing and other things. So this is comparable to a TV campaign running roughly 14 30-second commercials per person, or about one per day. So we're display ads and TV, think about it as it's about one commercial. We want to know what the effect is of showing a commercial on it each day over the course of 14 days. Each campaign is going to reach over 500,000 users, with many of them in multiple millions. The mean cost of the campaign was on the order of $100,000, the median $80,000. So the experiment is that we're going to be able to randomly determine who sees the ads versus who does not. And we're going to explicitly withhold people from seeing them by the flip of a coin. And so we can use this information from these experiments to calibrate the advertiser's problem. But first, a little bit of notation. This is pretty standard notation. We're going to have an individual be indexed by I. Y is going to be sales. We're going to be looking at both online and offline sales for any of the relevant advertisers. We are going to think about X as being 1 if the ads are shown, and 0 if the individual was not shown the ads. In general, in the experimental framework, that'll be a placebo ad. And then finally, we can think about having a vector of covariates. But for the sake of argument and simplification of notation, we're going to just ignore W and add the sort of condition on W caveat that all things will go through. Yes?
What do you mean by offline sales?
Sorry, the jargon. So offline means in store. So in the case of, let's just say that one of these advertisers is Macy's. It would be that we have access to their customer level sales records, which are which tell us both how much was purchased and where it was purchased, whether it was at Macy's.com online or through the internet channel, or offline being the brick and mortar or in store in their physical location. Does that make sense?
I think so, but so that means people who are paying cash and who are watching public IP address computers are on track.
Right. So this particular advertiser believes that they can track about 90% of their records properly. One of the main advertisers that we used in the study. So you're right that there is going to be some data joining problems, and so that's only going to make the advertiser's evaluation problem worse by introducing measurement error, which is going to make it even harder. So, but yes, that's true. We may end up with attenuated estimates. There are a variety of other sort of technical details which may also exacerbate the attenuation bias that may happen in experiments that we would have to deal with. But yeah. Was there another question? A placebo ad. Sorry. Yeah. So just to repeat the question, what is a placebo ad? So a placebo ad is an ad which is not the advertiser's ad that is unrelated to that category. So in the case of many of the experiments, we would either just withhold the advertiser's ad and some other ad that's in the queue would be shown, so some other ad that's not the advertiser's ad would be shown, or we would explicitly show them something like a public service announcement, like a Red Cross ad, so that we know that it was unrelated to the advertiser's sort of purchasing. The worst thing that we could possibly do for evaluating the absolute effect of advertising effectiveness would be to take Macy's and then put like a Bloomingdale's ad there. That would not be useful for an absolute measurement of ad effectiveness, but that would be useful actually from a competitive perspective if that's what would normally have been shown. But yeah. Yes?
What about, so do you assume that, so you're in control of whether certain individuals receive, you're in control of whether certain individuals receive one ad or another. So do you assume that the likelihood that they're going to encounter that ad by other means, maybe on some other website, that's like a random sort of orthogonal sort of thing?
Exactly. Yeah. So we're just going to assume that all other advertising is happening, and every single one of these campaigns will, in some sense, be estimating a marginal effect, sort of the marginal return to advertising.
So does that also assume that that any shocks affect all of the units, the experimental units, equally? Like, for example, if Macy's does something in Florida in like one, and you're drawing from units that are not only in Florida?
Yeah. So in this particular case, in most of these experiments, we actually did randomization at the individual customer level. And so there are a variety of caveats, like it could be that a husband and wife are both in the experiment, one ends up in the treatment and the other ends up in the control, and there could be some cross-contamination that goes on. So again, all of those effects are only going to make the estimation problem even harder and are generally going to attenuate the actual treatment effects. So for the purpose of this talk, I'm not actually going to present any absolute treatment effects. We have several other papers which go into greater depth on those, on actually providing an estimate of what is the return to advertising. Does that answer the question?
Yeah.
Okay, great. All right. So we have this notation. I'm glad we were able to pause there a minute so that people could chew on a few letters and make sure that we know it's there. In particular, because we're going to look at this regression. Pretty simple. It's sales on ad exposure, where ad exposure is potentially exogenous, or it may be endogenous if we did not explicitly set up an experiment. And then beta is going to give us the average treatment effect, or the average sales difference between an exposed and unexposed group. Okay, so in an experimental study, the exposed group is the treatment group, the unexposed group is the control group, and we have a very clean, it should be orthogonal to everything that matters, and also many things that don't matter. In an observational study, we were going to have the exposed group be people who are endogenously exposed, meaning they either selected into a particular web page, they visited their email that day, or perhaps there's even a targeting algorithm running in the background which has selected them as being more important for this particular ad or not. And then the unexposed group is going to be a pseudo control, and necessarily. The pseudo control is not going to have been targeted via whatever algorithms, or is not going to have any of those additional. It won't have any. It'll have, in some sense, a complementary selection, in that it was not selected. So we're going to just take a quick look at the R-squared in this regression. So economists, we never look at R-squareds. Like R-squareds don't matter. We're taught this in sort of our introductory econometrics classes that the quality of a model is not in the R-squared. Well, the problem is that there's actually, it does matter in this case. So we can write the R-squared as a pretty simple function of the treatment effect, or the difference between the exposed and unexposed groups, delta y bar, over sigma. And so, we want to calibrate this number using some of the numbers from the experiments. So we're going to use the 19 retail sales experiments to calibrate it. These are retailers ranging from budget to high end. So again, many of them are household names. I can't disclose the names just because of confidentiality reasons. So let's just calibrate it using a median example. So the median advertiser in our sample had average weekly sales of $7, standard deviation of sales of 75 at the weekly level. The cost was 14 cents per customer, and then the ROI goal that we were looking for was essentially a 35-cent increase, which would have yielded a 25% ROI. So essentially a healthy ROI, and this is kind of the standard practice in the industry of how you would think about the problem. You would be seeking some sort of ROI of that, generally of much larger magnitude for some strange reason. But in the end, our goal is to increase baseline sales by 5%. But we're faced with a real problem here, that the standard deviation is 10 times the mean. Another way of saying that is that the coefficient of variation is 10. Again, that's a statistical piece of terminology that we don't talk a whole lot about in economics, but here it's going to matter. So we have the R-squared equation. What does that mean? It means a successful campaign is going to have an R-squared of 5.4 times 10 to the minus 6. So this is not the type of thing you want to see in a scatter plot. Like, if you draw a scatter plot of this, it looks pretty awful. We used to have one in the presentation, but people couldn't understand it because it didn't make any sense. There's just a flat line and a bunch of noisy data. So some observations given this information. First of all, we're going to need very, very large samples to distinguish a profitable campaign from zero effect. And even experiments with 1 million subjects in each group can be underpowered. So just enormous experiments. But an even bigger concern is that selection bias in observational studies where there are omitted factors with partial r squareds on the order of 10 to the minus 4. So again, endogeneity on the order of 10 to the minus 4 is a full order of magnitude more than the treatment effects that we care about. So we could potentially have some pretty big biases lurking in observational studies of ad effectiveness. So the selection bias can swamp the actual true ad effect because it's so muted. And this is a concern because ads are by design not delivered randomly. Otherwise, we'd have to tear down some marketing business schools and some buildings there just because they're not doing their job. But they are doing their job. They're teaching some useful things, but this problem is really hard. So the fundamental question is, can an observational method ever be sure all selection effects have been eliminated down to such a small fraction of variance into the dependent variable? And sort of our argument is that no, because even though experiments are unbiased, but they're very noisy, we run into this challenge that observational methods can actually be quite dangerous in terms of providing biased estimates, which then people make multi-million-dollar or perhaps even on the order of billions of dollars of decisions and that are completely erroneous and mistaken. So for those of you who saw Steve Tadelis' presentation a couple months ago, you'll know that I'll talk a little bit more about it later, but I think that's pretty much a great example of how large companies can potentially be making very big mistakes just because they're in this type of environment. So let's strengthen a straw man. We have a quote from Majid Abraham from the 2008 Harvard Business Review. He says that about measuring advertising, he says, measuring the online sales impact of an online ad or a paid search campaign in which a company pays to have its link appear at the top of a page of a search results is straightforward. We determine who has viewed the ad, then compare online purchases made by those who have and those who have not seen it, essentially comparing exposed to unexposed. So there it is. It's in the Harvard Business Review. Apparently advertising effectiveness is actually pretty easy to do. We just compare people. I disagree. So let's get into some more detailed results here. So we're going to present some raw statistics from our advertising campaigns which evaluate the hypothesis sets given that the alternative is true. So we're going to have a null and we're going to have an alternative, and we're going to ask the question, do we have power to distinguish between them? So what we're going to do is draw the hypotheses closer and closer together so that we can think about approaching what would be optimizing for the firm, drawing closer and closer to smaller ROI tolerances. So just to give you an overview, so this does look really daunting. I'm going to walk through just a couple of, I'm going to walk you through the columns sort of one at a time, but I think this is a really useful way of looking at the data. So on the left-hand side, we have the retailers and the financial services are indicated by R and F, and we have 19 retail experiments and 6 financial services. These were run between the years 2007 and 2011. And we use a variety of methods to get more efficient estimates. So we're going to use covariate data. Sometimes we had some data available, other times we had other data available. But we're going to try to get the best estimate that we can possibly do without introducing bias. The campaigns ran anywhere between 2 days and 105 days, with the median being roughly 2 weeks. And the cost, as I said before, is on the order of $100,000 on average for the campaigns. We have most experiments involving more than 1 million unique users, with a large share split between the test and the control groups. We haven't done any sort of optimal experimental design. You might notice that these aren't split 50-50, or they're not split according to what you might think would be optimal. The reality is that advertisers who hold the purse are the ones that actually get to impose constraints on us as we perform research. So in some cases, they don't want to sacrifice a very large control group, which would have helped statistical power because there's an opportunity cost associated with that. If we don't show ads to people today, then we don't get sales today from those people under the presumption that advertising is effective. So then one of the other major key insights that I mentioned, but you can see in the table, is that the median average sales is around 850, but that we're going to have the coefficient of variation, or the ratio between sigma and mu, be about 10. Okay. So how do we understand this coefficient of variation? So what we want to look at is a scatter plot of the different campaigns. So each dot here is one campaign. The horizontal axis, we have the campaign length in days, and the vertical axis shows the standard deviation mean to ratio, standard deviation to mean ratio. And what you might expect is that shorter campaigns are going to have more volatility than longer campaigns, just by the nature that sales are roughly independent. So we're going to see that the standard deviation is going to follow something kind of like a square root of t, which you might expect. As you have more days, the actual effects are going to be somewhat independent, and that will help us bring down the variance. Okay, so. But then we want to look at the actual power of these particular experiments. So we have some descriptive statistics. Now we're going to look at power. So one thing to note is that the standard error of the ad impact regression is going to use all covariates to improve power. And you'll see that the standard errors are sort of on the order of pennies to dimes. The costs, however, are on the order of a dime. So we're going to have standard errors and costs which are of the same order of magnitude for many of these. So again, these costs are on the order of showing a person perhaps 4 to 7 Super Bowl ads, or as I said earlier, roughly 10 to 15 regular TV ads. So the confidence interval radius is going to be pretty wide on sales, but the more important one is the standard error on the return to investment. So the median standard error on the return to investment is 26%. The mean is about 62%. So this means that when we want to evaluate these hypotheses in terms of a return on investment, we're not going to have very great precision in order to decide whether it's 5% or 10%. And so let's proceed and discuss that a little bit more. One thing that to note is that the more you spend, the more precise your estimates are. So we have the ROI standard error on the vertical axis and the actual campaign cost per person on the horizontal axis, and we see connected lines for each of the different retailers. And we see that the more you spend, actually the more precise your ROI standard error will be. Some of that it's reasonably mechanical. It's that if you spend more money, you have a larger base against which to compare. So you can think about it in a regression sense as kind of like having more leverage. So in the end, just back one sec, note how large the ROI standard error is for campaigns that are only evaluating differences on the order of 1 to perhaps 5 or 10 TV commercials. The ROI standard error is on the order of 100%. So that means that we'll be able to say that the commercials, sort of a series of commercials shown to people, had an effect of, say, they cost 10 cents per person. We'll be able to say that that's 10 cents plus or minus 20 cents. In other words, we'll have absolutely no idea whether it was profitable, let alone whether it was optimal. So the takeaway here is that estimating the sales impact function is going to be much harder to estimate as we move towards lower costs, as we move towards the origin. So do we have the power to reject a minus 100% ROI campaign? In other words, did the ad do anything? Well, when we take the expected t, given that the alternative is true, which is that the ads broke even in this case, we're then going to take a look at, we're going to try to find campaigns that have at least an expected t statistic of 3. Why do I want an expected t statistic of 3? Well, it's because that actually, it's sort of a rule of thumb that I really like that says that you have a powerful test. If in advance you know how big the effect size is that you're looking for, if you can calibrate your experiment so that it has an expected t statistic of 3, you'll have a 90% chance of rejecting the null with a 5% one-sided test. So it essentially is a way of saying you have a reasonably high-powered test. So we present what the expected t statistic is for each of the campaigns, and then we present in this column the data multiplier, or in other words, how much larger would the experiment need to be in multiples of the experiment in order to give us a powerful, an experiment that has an expected t statistic of 3. And we see that in that case, we can think about multiplying the experiment as either running it for longer while continuing to increase the spend over that time range, or you can think about running the advertising to over more people, perhaps finding some new sample that's similar to the one. And so we think about running either the same experiment over and over again, or somehow showing more, finding more people, or basically how much bigger does the experiment need to be in order to be powerful? Yes.
Just partly clear. Partly just a clarification question about the data itself. When you link up advertising to purchase, how long after the ad run do you actually wait? And so there isn't it strikes me that there's not comparability between running a campaign longer for a larger, more expensive expenditure, which may actually be done less frequently or require more thought process and more search. And so is it that, anyways, I don't think there's a comparability. And could you just talk a little bit about the data for how you actually match up purchases?
Sure. So the evaluation window is really important. I will actually talk about it in greater depth towards the end of the talk. So you're right that the evaluation window definitely will matter. And for sales, just to quickly respond, for most of these campaigns, when we actually do the measurements, we're going to look at during the campaign, during like the 2 weeks that the ads were being shown, and then maybe a week or two after. Some of that's due to convenience. The advertisers want answers back as quickly as possible so they can then act on them. Or it could be that there's also some additional statistical problems, which I'll talk about towards the end. Okay? All right. So again, do we have power to reject minus 100% ROI for these campaigns? 9 out of the 25 experiments lacked the power to detect anything, meaning they were completely underpowered. And so you can say, well, Randall, you were kind of dumb. Why did you run those experiments? Well, the reality is that sometimes we didn't even have the sales data in advance, and we couldn't communicate properly to people how to compute a standard deviation so that they could actually tell us the calibrating, the baseline numbers that we would normally input into a power calculation. There were some cases where where basically we had to give them a report because they wanted to buy advertising, and we wanted to make money. So what we did is gave them the opportunity to run the experiment. We tried to do the best with what we could, subject to their constraints. So what does that mean? That means the minority of the advertising experiments do not answer even the influence question. Did the ad do anything? But a majority, 16 out of 25, can answer this question. But this is generally where the literature is going to stop. So Kyle Bagwell has a nice review article on the economics of advertising in the Handbook of Industrial Organization if you want to take a look. But this is basically where most people stop. Nobody thinks about optimizing because, well, it's kind of crazy. But we say that rejecting a minus 100% ROI is a pretty low bar. Right? Did the ad do anything? Well, that's not exactly what we're going to teach our graduate students or MBAs or undergraduates. So let's try to draw these hypotheses closer together. Let's think about break even is the null. Let's say we sort of know that we're good at that the advertising has to do something and that we're pretty good at ensuring that it's cost effective. And we want to be able to identify the really profitable campaigns, the ones that are generating a 50% ROI. So this is break-even versus very successful. And in our model, negative ROI estimates are generally going to be a stronger call to action than positive ROIs. So you're going to generally have a little bit more information on them, or as in the eBay's case, there's a pretty strong argument that when you get what looks like a pretty negative ROI, there's going to, at least you know which direction to go. You know to decrease your advertising spend. So what we find in this sort of harder case, again, we have hard, harder, hardest, and crazy in the far right. We'll get to those. But in the harder case, only 3 out of the 25 experiments can meaningfully detect this difference. So we have 12 of the experiments had an expected t-statistic between 1 and 0. 5 were between 1 and 2. 5 more were between 2 and 3. So the median campaign would have to be 9 times larger in order to be able to distinguish between a very profitable campaign and a break-even one. And for some of the campaigns, it's in the hundreds. So 5 campaigns would have benefited from modest expansion on the order of 2x in order to be powerful. And in the end, only 3 could determine if a very successful campaign was worth it or not in advance. So basically 50% versus 0% ROI is a far cry from finding the tangency we talked about earlier, the profit maximizing one. So now let's just strengthen it a little bit harder. You guys know what's going to happen here, but the way to think about this is we're just asking, suppose you have a null hypothesis, which is that the ads were not profitable, they were just break even, and we want to look for a 10% difference. Maybe we want to know 10% on either side, or even more generally, maybe we just want to compare the ad effects, and we need a resolution on the order of 10%. So all 25 fall short. Anybody could have guessed that given the past column, but 21 out of the 25 were so bad that the expected t-stat was less than 0.5. So these experiments are essentially hopefully underpowered. They're going to require well over 10 times the size of the experiment in order to be able to talk about anything related to optimizing. So even the most powerful campaign would have to be 7 times larger to give us a powerful statement about perhaps a resolution of plus or minus 10%. And so in the end, the median would have to be 61 times larger. Well, just to make sure, yeah, the median would have to be much larger, and the mean would have to be over 1,000 times larger. So it seems kind of crazy, right? So what about 5% tolerance? Well, this seems kind of silly at this point. You guys are saying, well, yeah, of course, it's going to be terrible. But we assert that this is not a straw man. This is actually something that matters, and it's a pretty hopeless situation. So what do we actually teach undergraduates and MBAs? So now here's kind of like the kicker. What about annualized 5% tolerances? Okay, so everything I said was kind of relative to 2 weeks. For the median 2-week campaign, we have to multiply the crazy column by 26 squared, meaning if we wanted to know on an annualized basis whether this campaign was worth running, assuming that the cost of capital is you pay at the beginning of the campaign and you get the yield and expectation by the end of the campaign, you're going to need experiments on the order of 676 times larger. But at least that makes the problem that much harder. So seems kind of crazy, right? Well, that's actually too crazy even for our paper's tables. We decided that nobody was going to believe us if we included it. So what do you guys think? Too crazy? Some people think it's too crazy. So, all right, so now we need to determine the ROI target. Knowing all of this, you might say, well, this seems kind of silly. Well, let's just talk about it a little bit more carefully. Okay, so we have our advertiser's problem, and what we know is that over on this side, suppose you get a point estimate that says that the average ROI, which is again going to be sort of the ratio between gross profits, which is this product here, and cost, suppose you were able to show that ratio is less than 1. Well, then, maybe it's noisy, but at least you kind of know that you should decrease your advertising. You know what to do. There's a pretty straightforward decision which says scale back your advertising a little bit. In this range, we actually have pretty hard decisions because what we observe in this entire range is an average positive ROI. But we don't actually know that we are above the optimum. It could be that we're still below the optimum. We don't really know whether we're here or here unless we can actually estimate a first derivative of this function. Or first derivative? No, I think we need a second derivative. No, probably first derivative. But anyway, first derivative is pretty hard, and I'll talk about that in a minute. But essentially, in this range, like I talked about before, when we scale cost close to the origin, the standard deviation of the ROI is just going to blow up because we're looking at essentially very little changes in cost, and we want to compare it against a very noisy difference in sales. So we need to establish what the ROI target is. In order to do that, we need to estimate this beta function, which was the sales impact function. So think about it, we can maybe use noisy estimates against splines in order to do this. So let's just take a simple example and see what we would do. So again, look at the impossible measurement example. So now I'm going to put some pretty reasonable confidence intervals that are very similar to what we see in our paper on this. What do we see? We see that the average sales effect was, in expectation 0 for 0 ads, so we can sort of put it there, but we still have to estimate what the average sales was for this. Then we have to estimate what the average sales is from actually advertising at the optimum. And in the end, you can draw almost, if you think about these as normal distributions, which they generally should be, assuming regular asymptotic properties, you can almost draw any upward, downward sloping line here. There is some restrictions on what our point estimates are, obviously, but this really leaves a lot of leeway for trying to find the point at which this slope is equal to the slope of the curve is equal to the cost function. So then we can think about extending this even further. Suppose we had another estimate that was out here. This estimate can barely say that there actually is an effect of the advertising if we just compare these two. Maybe you need a square root of 2 floating around and then you wouldn't be able to. But the takeaway here is that even if we were thinking about doing this as non-parametrically, we would have a very noisy set of curves that could all fit through here, and we wouldn't have a very easy time saying anything very rigorous. So why is this? Well, if we look at just the variance formula for the ROI against sort of a change in C, if you think about change in C as the horizontal axis, and I'm going to abuse some notation here relative to before, but in the end, we're going to be looking for differences in the function divided by differences in cost. So the interesting thing is, we all know calculus. Delta C going to 0 is what you would use to estimate what the marginal effect is for a marginal campaign. The problem is delta C is also pretty close to 0 for standard campaigns in the world of advertising. We're talking on the order of pennies. So what does that mean? That means that for very, very small C, we're going to have ridiculously large variances on the return to investment. So maybe you want to ask the question, is the ROI declining? Maybe that seems like a more tractable question. Well, it's actually not. It turns out that estimating if you want declining ROI, you have to estimate that second derivative, and you have an additional delta which runs in front. And it's even harder because of, first of all, if you're running an experiment, you're going to have to split your sample into more pieces. You're going to have 3 pieces instead of 2 under the simplest case. And then delta C, you're going to have to split probably roughly in half. So now you're looking at an even harder problem. So that's kind of our problem. Seems kind of a mess. So in the end, we can draw many shapes of ROI curves through these bounds. So, but this was just a single curve, right? Like this was just our stylized example. What if we needed to compare target groups or creatives or other dimensions? We were varying the intensive margin there, which is how much advertising, but what if we want to compare how we advertise? Well, in the end, we're only going to be able to detect massive differences on the magnitude of plus or minus 100% ROI because we're basically doing the same problem. We're comparing ad effect in one group to ad effect in another group. But even bad creatives to the wrong target audience are going to generate hopefully some effect. So let's say you show the wrong ad to the wrong people. Maybe some of those people actually respond and buy, but it just wasn't as cost effective. That's going to be a positive effect relative to the effect of not advertising, which is 0. So in essence, it's actually going to be a harder problem, and we're only going to be able to separate things that are massively different. So if you wanted to know whether one particular display ad was better for your target population versus another, you're not going to be able to do that with respect to sales unless you have a massive sized experiment, or one of those different display ads is way worse than the other, or perhaps way better as well. So in the end, such optimizing is in the realm of hardest or more likely crazy. This is just really hard. So, but again, I wish it were that simple, but we have large firms advertising both out of home on TV, doing online display advertising, online search, doing a whole bunch of other things. And as was asked before, essentially, we and everybody else in this literature are essentially always going to assume that these factors stay constant, which is okay if we're thinking about measuring a marginal effect of the campaigns. So now let's sort of play devil's advocate. So we did all this crazy stuff, and you guys are probably thinking, Randall, you just beat a dead horse, right? Like there's so much that you just basically said it's impossible to measure advertising, but maybe you were just goofing up the whole time. So hopefully we'll present a few arguments here, but I'm happy to field other arguments as well, okay? So suppose you're a referee. You might ask, well, won't computational advertising solve all of these problems, right? We just sort of hook a computer up to the system and companies like Google and Yahoo and many of these other large firms, or even some of the smaller firms that are creating targeted advertising systems, maybe they'll be able to solve all these problems. So in the end, computational advertising, as it is known today, is essentially automated targeting, where the target is created by generally taking people who buy and people who don't buy, and then aiming the ads at the people who are buying, presumably because that indicates a higher sense of interest or focus on whatever the advertiser wants to sell. So machine learned systems are going to be optimizing against these conversions or these purchases, people who are already buying. So the key parameters are still going to be set by humans, so there's still an inference problem. We have to set things like bid, per person spend cap, total spend, conversion metrics. Like there's still a decision problem that has to be done by individuals at some level. So a fully automated system would still have to do the exact inference, via automated experimentation that we've described in this paper. So while they may be able to do it more efficiently, maybe a little bit more quickly, without as much dead weight, because organizationally it was very difficult to carry out these experiments because there's a lot of people and systems to sort of put together, and there's a lot of people who want to make decisions because it's not, for whatever reason. So in the end, what we find is that in the paper, you can take a closer look at this, but we find that targeting can help or hurt the inference power. Yes, when you target, you end up shrinking the sample size. However, you may end up you may be able to look for a larger effect then, because you would expect the effect to be higher among people that are more interested in the ads. So maybe another question you have is, maybe these are just weird firms. I said they're big retailers, but maybe they're not normal firms. Maybe this isn't how the rest of the world. Maybe Yahoo and all the firms that I was working with just happen to be really weird. Well, let's take a look at automobiles. They're a hugely advertised category. On the order of 1 in 12 TV ads is for I think pickup trucks. So there's massively advertised. And what we can do is look at public data on sales. And what we find is that what retailers were learning in weeks, if you sort of do all of the power calculations that we did for these advertisers online, we actually find that automakers, against the purchase of large vehicles that people rarely make, it's going to take automakers a year to learn that same amount. So in some ways, their inference problem is actually an order of magnitude harder. So maybe they're not the only one. We have electronics, jewelry, credit card signups, and so forth. They all have similar consumption patterns. And because of that, we're also going to have similar ad effectiveness problems in terms of evaluation. And so, and a shout out to David Brockman. I'm never going to pronounce your name right, I'm sorry. He did a pretty cool experiment recently that I saw last fall, and basically sort of taking some of the results of his study, which was not the focus of his paper, led us to be able to understand that even politics is not going to be exempted from this. When we take a look at establishing economic bounds on the cost per vote from online display advertising, in this case on Facebook, it's going to take millions and millions of people in order to get reasonable estimates on how much a vote will cost. Perhaps the only candidates that will be able to do this are on the order of congressional officers or maybe even the presidential campaign itself, using sort of the, if we believe some of the results that we have here. So maybe we've miscalibrated it, but I think what we've done is actually reasonably fair. So perhaps these experiments are just too small. Well, to address that, we have what we call the Super Bowl impossibility theorem. So it's not really like a theorem in any sort of formal way, but what it does is it establishes two different bounds. One is a detectability bound for a firm. How much advertising can a particular firm detect, and a sort of an accounting bound, which is how much advertising can an advertiser basically afford a Super Bowl ad. And what we find is that most firms that can afford the Super Bowl ad can't actually detect the effect, even in an ideal experiment. So if you're big enough to afford the Super Bowl, you're not big enough to detect anything. An aside to that is that if you are big enough to afford multiple Super Bowl ads, well, you might actually be able to detect something. So there's these bounds, again, they're not exclusive. They don't say you can't measure anything, but they do say that only under certain conditions and certain amounts of spend might you be able to do that. So again, why not just use very long evaluation windows, or how do we think about choosing the evaluation window? Well, let's just take a campaign. We have 2 different points in time, a start and an end date. And then we perhaps have to pick a point at the end of the campaign to say this is when the data needs to be delivered. And so generally what we're going to do is we're going to measure the effects of the advertising from the start of the campaign until some short window following the campaign. Again, it depends on the purchase cycle of the product and also the time sensitivity of whatever we're doing, but the trade-offs are actually pretty meaningful here. We could potentially shorten it. That would be kind of silly. We generally want to ensure that we're capturing all of the effect. That might introduce some bias in terms of the total effect of the campaign. So some people have asked, why not just take it all, right? Like, we know that the ads probably are still doing something out here on some fraction of the population, that there's some effect there that we're missing. So we must have downwardly biased estimates. We've missed some of the effect. Well, there's 2 problems with this, at least. The first problem is the value to acting on information that I mentioned, that advertisers, once they've learned something, they want to be able to use that and then leverage that today and not have to wait a long time. The second thing is that statistical challenges are actually going to increase with time. And so why is this? Well, it actually turns out in this case that more data does not actually equal more precise inference. And it's pretty straightforward why once you think about it, although this does sort of go in direct contradiction to what we might think, that larger N should always be better, right? Well, in this case, the reason why is that with time, although the cumulative effects are increasing, meaning we're getting more of the ad effect as we go further in time, we're also expecting the per time period effect to decay. So there's various reasons why this might be. You can write some models. But this is an operating assumption. Otherwise, if it never decayed, we might expect the effect of the ads to be infinite, in which case that would be completely irrational with current amounts of spending, and they should be spending a lot more money on advertising. So in the end, more data actually leads to decreased signal, and that decreases our signal-to-noise ratio. So we have to make a judgment call, and you can potentially use some more robustness checks to evaluate it, to see whether you think that you're missing a large amount of the effect, or basically the trade-off between variance and bias here. So this is just a necessary decision that has to be made. So we make it this way, understanding also that given the amount of noise, the greatest signal is lying during the campaign evaluation period, and so that's where we're going to look for the most statistically precise estimates. So another question is, do advertisers agree with anything that we're saying? And maybe it's not fair, but some recent evidence from one advertiser agrees. I say it's not fair perhaps because, Steve Tadelis and Tom Blake and Chris Nosko are also economists, so maybe they're biased. I don't know. But basically what they did, those who were here 2 months ago, they estimate the effects of search ads on profits. And what their experiment confirmed very precisely was that biased observational methods could be rejected as providing reliable estimates under certain settings. In essence, observational methods yield massively biased results in their case. And this was making a huge difference in terms of the decision making. Their experiment also confirmed, albeit somewhat imprecisely, that an ineffective ad campaign could be rejected as profitable. So in the end, their confidence intervals there are tremendously wide, though that's not perhaps very surprising given what we've seen so far. And all of this was in spite of having varied millions of dollars in advertising spend in order to get their estimates, which still sort of are on the order of magnitude of an ROI of minus 50% plus or minus 50 or 60%. So that's kind of the challenge. So just to sort of conclude with a brief discussion, how am I doing on time? Just okay, so like five-ish minutes. Okay, all right, we'll wrap it up pretty quick here. So the implications for the market, we have heterogeneous beliefs are some things we might expect. And what we see in the data is that these sort of are borne out. Delta, for example, spends 2 times the amount of advertising relative to United against basically similar revenue. And this is in spite of Delta having a lower profit margin. So maybe something's weird there. I don't know. Like maybe Delta is fundamentally different from United in ways that I don't see. We see Wendy's, Burger King, Dairy Queen, Jack in the Box. It seems that Wendy's and Burger King are engaging in a high advertising strategy, and Dairy Queen and Jack in the Box are engaging in a low advertising strategy. Maybe there's a strategic model that can actually explain this. Maybe it's just that nobody has any idea, and weird beliefs can persist in spite because there's very little information and feedback validating or rejecting particular beliefs. Yes.
Have you looked at the CEO, the function of the CEO?
Mm-hmm.
Function they came up from. So do Wendy's and Burger King have CEOs that came out of marketing and sales?
Okay.
Have you looked at that?
I have not looked at that. If that's the case, that would be really interesting, and that would certainly be consistent with perhaps beliefs just being very hard to pin down and to establish. So that could be some really interesting research to do in the future. So another example: E-Trade, Scottrade, and Ameritrade. We see 2%, 8%, and 12%. There's just very wide variety in terms of actual amount of money, actual amounts of revenue that these guys are spending on advertising. Why is it so different? Well, maybe it could be, again, maybe there's something we don't observe. It could just be that they're crazy. So this is all advertising using Kantar's ad spender tool. There's a chance that we may have that. There's a chance that when we do this, we may miss some things, or that we may.
TV, I would have thought would be the other way, but just mass advertising, I thought would be the other way for us.
You were saying you would expect.
Television, mass market, not targeting. I don't know what I mean.
So is the question, you would have expected E-Trade to be spending less, or
They're less visible.
they're less visible?
Yeah. So I'm just wondering how they were spending money.
So E-Trade is also spending in the Super Bowl, and like they have their E-Trade baby commercials and things that many people might have seen. Just from experience, I don't really watch that much TV, and I'm really not the average consumer. I'm kind of weird. I accept that. But these are kind of what we see. So there is a chance that there might be something up with this data. We've gotten it from sort of a standard industry type report, and maybe we missed something. But we still find it surprising that these types of magnitudes would come out of that. So we consider the data that we got it from is sort of industry standard and should be considered reliable. Okay, so maybe there's a value for reputation. It could be that maybe it takes a decade to learn how advertising actually works, and then agencies are able to then carry this information along. It could also be that maybe now only large publishers like Google, like Yahoo, can even offer experiments on the order of millions of people. Maybe this is a new competitive advantage of scale. That's going to have some market implications on the diffusion of information about advertising. And finally, are there some other similar situations? I love this example, so I'm going to conclude with it. So vitamins, first of all, the question is not do we need vitamins in our body? The question is, do multivitamins or supplements as we take them, do they do anything healthy for a healthy individual? Or are they just kind of a nice placebo pill? So there's some basic research that was very expensive to do. They do tens of thousands of people. They've taken over 10 years to complete. And these vitamin trials essentially tried to detect what the effect is of taking vitamins on health outcomes for which we expect there to be possibly some sort of mechanism. And they find point estimates that are near zero. They say, well, vitamins could help. They could hurt. For cancer, it's plus or minus 10%. For heart attack, it's plus or minus 20%. So now let's stand back and let's say, well, what are the implied economic confidence intervals here? Yeah, we were able to bound that it doesn't kill tons more people, and it also apparently doesn't save a whole lot more people. But what does that mean from an investment perspective? It says that in these studies, they spent about $2 million at today's market prices for vitamins that was what the people were actually consuming. And the return was plus or minus $96 million for heart attacks alone, using a recent total economic cost of a heart attack on the order of $750,000 or $1 million that came out of a study from Harvard. So the cost of a heart attack is $1 million. We have basically plus or minus 96 million. So what is the ROI there? We know that the usefulness of taking vitamins is a plus or minus 500. Shoot, I'm not even going to say it right. 5,000%. So every time you take a vitamin, maybe it costs you like a nickel. It could be killing you by 250, or it could be helping you by 250. So I don't know. I don't think we're ever going to know. I think it'll take billions of people actually to do this. Do your own power calculation. So what that means is that this $20 billion industry could be grossly under or overvalued for what it's producing. So just to conclude, the data is stacked against advertisers. The signal is tiny relative to the noise. Even in a simple framework, causal effects are going to be hard to estimate, and observational methods are going to require quite a bit of faith in the modeling assumptions. So it's not impossible to estimate ad effectiveness, but the inference problem that is facing advertisers really takes us out of our textbook case of optimization. So we should expect imprecise or mistaken beliefs, and the market will change as information quality improves. Thank you.
I have two related questions. The first is, to what extent are your results driven by the highly skewed, highly variable data of purchasing? And if you chose something else that had greater stability, such as just willingness to purchase, would this change your results? And the second question is, even given your results, you had the nice slide where you grayed out basically the confidence interval overlaid on top of the price. If I was faced with a choice, I might reject the hypothesis that I could, at a given level, reject a zero effect. But the bulk, like if I thought of this from a Bayesian or decision theoretic perspective, I know where the bulk of my posterior is after the experiment, and therefore if I was faced with this choice, yes, I might be getting very little for it, but the bulk of it is suggesting that I might be getting something very significant. And unlike vitamins, which two things about that is, one, that was actually symmetric around zero, which is obviously more troubling. The second thing is, I'm not sure any of us want to do something that is actually voluntary that could actually decrease. I think we have a different loss function when we think about our own lives than we do, say, accepting a small amount of density below zero on advertising compared to actually a pretty significant upside. And I agree that confidences are wide. So,
okay, so to the 2 points. So the question about whether it would make a difference if we didn't use sales volume and instead did something like purchase probability, for example, or transaction probability. It turns out that about the right way to think about this is in that number 10, you can think about it as the product between two variances, which are the variance from the probability of purchase and which is generally going to be a rare event relative to the scale of the data we're talking about. When you go to a place like Macy's, you're not going there every week. You're going there perhaps once a month or once every 2 months or maybe even once every year. And it turns out that component of that variance is probably on the order of 3. And then the other variance, which is conditional on purchasing, how much do you buy? That number is probably also on the order of about 3. So it perhaps makes the problem a little bit simpler, but it also obfuscates what is the actual ROI calculation. So there's a trade-off there, but that's totally fair. Your second question was
sort of, given if you thought of it in a decision theoretic point of view.
Yes, okay. So sort of the question, what if I treated it as though I were, from a decision theoretic perspective of using like a Bayesian posterior, I would say that so with the particular example that I showed with the confidence intervals, again, those were sales effect confidence intervals. If we had to compute an ROI confidence interval, again, the ROI confidence intervals would be tremendous. So we're not talking about just a little bit of probability of the ads. So yes, there was perhaps a small probability that the ads did anything that was below zero. But relative to the cost, it's just really hard to evaluate because we actually need, for that cost effectiveness calculation, we need confidence intervals that are really orders of magnitude, perhaps an order of magnitude or two smaller, so that we can actually say something meaningful. And that's going to require much, much more data. So while yes, if you approach it from a Bayesian perspective, you would update. You would say, I think the effects are kind of positive, the ad's doing something. On the ROI side, it would take you hundreds, maybe thousands, maybe tens of thousands of these experiments in a stationary environment for you to actually believe that what you did was profitable or not. And so, assumptions about stationarity, and again, costs are linear. That means you'll have to spend tens of thousands more in order to learn that. It just begs the question, is there enough stability in the environment? I mean, just over the 5 years that I've been at Yahoo and Google, we've seen the way that advertising is being done in the industry is just radically changed as things like search retargeting and actual targeting models using sales data and joining, like there's a lot of things that have changed, and understanding how stable that could possibly be over the course of 5 years and seeing how unstable it is sort of begs the question, how do you even operate in a more dynamic environment than the model we have here? So.
I'll ask Jonathan's question a slightly different way. So like in a Bayesian, God knows I'm not a Bayesian, the Bayesian framework, priors going to have to do a lot of work. But one can say the advertisers have priors since they're spending so much money. So, if I had a prior that have a point mass at 0, and if it's not 0, it's a uniform distribution of the ROI, of the effectiveness. And, it's not quite right. It's not going to be uniform forever. But if that's my prior, it does have the feature that any data that pushes me away from 0 really ratchets my expectation up a lot, right? But in that kind of prior, I'm going to have a lot less information is going to be informative to my decision making than it is in the classic framework, right? It doesn't get rid of the problem you mentioned, but it does mean that if I had a prior that does some work, and that's a goofy one that does work for all point masses away from 0, that I'm gonna learn something, right? And in your own data, the priors are at work, right? Because they're spending so much money at this, et cetera, et cetera. So I don't know if you've done the calculations for various informative priors on how difficult or easy decision making is under them.
Okay, so you're asking how much might your decisions change depending on what your prior is?
Well, what I'm saying is if you have an informative prior, and these actors seem to, since they're spending this money and this uncertainty, how bad is then the situation?
Okay.
Right. In the classical framework, it's bad, and so there's no free lunch in life. So the only way the Bayesian thing's going to get anything is if you have some information.
Yeah. So suppose the advertisers already knew what they were doing.
I'm not going that far. Say I have my prior is a point mass of 0 and a uniform distribution, and I don't know whether. So I think there's a lot of 0 effects, and I think if effects are significant, then I think the ROI is pretty good. And say I have a 50-50 over those two worlds, right? That's going to mean that in a lot of experiments, I'm going to have all the point mass that's bound away from 0, it's going to really ratchet me up quickly.
Okay, so you're saying if it turns out that there are two states of the world for the actual effectiveness of advertising, it either does nothing, and sometimes it's just going to do a lot, and that's going to be really informative.
That's just my goofy prior.
Okay.
Right. How bad is my information? How badly can I update? I mean, can I update?
Yeah. So I would say that certainly will help you on the initial increasing your ROI side. You'll be able to see examples where things are very, very effective. But at some point, if you're thinking about it from an optimization perspective, there's always going to be a marginal campaign, some sort of marginal effective advertising, or some tweak that you could do to even something that is really effective, and you just won't ever be able to do that optimization because the resolution, the ability to distinguish between something that's really effective and something that is like 5% more effective or 10% more effective, even if it's like an 800% ROI, you may still not be able to optimize given that you know that. And the step is that if it's getting 800% ROI, you should spend more. And that sort of economic argument just says you aren't optimized, and that's the only reason you're seeing anything that's really out of whack. So I agree that might change the way you think about things. Yeah. Yes.
So one of the traditional assumptions in this approach is that the units are independent, and a lot of people believe, and I think there were some talks in this series, that people are actually heavily influenced by their friends, what their friends do. My wife bought a car not because of anything to do with the car, it's because her friend had a Audi Quattro. And so, I mean, this is a really strong effect right now. It's probably getting stronger because of, you know, the way Facebook's targeting and so on. So, I mean, the trouble is, there's two problems. One of this, the unit randomization is unnatural. It doesn't represent a real intervention. The second thing is, well, the unit's not independent, and so the estimates, and it's destroying the signal in a sense, because that, you know, reinforcement within groups is being, you know, broken. Contrasted, say, with trying to basically take groups, try to group people somehow, even demographics if you don't know the social network, randomizing across those units, which then become independent, which then have the reinforcing features. Seems like that's strengthening the signal and also reducing the sort of bias from the dependence between the units.
Sure. So there's a couple things to say to that. One is, if these effects actually do exist, then there's a couple of implications from them. One is that when we do these types of experiments, yes, we're underestimating the effects. Here we didn't present anything that had anything to do with the actual point estimates. All we did is with respect to the variance. So I think what would actually generally happen in the case of your wife purchasing a car as a result of having had an interaction with somebody else who had purchased a car, that model might actually behave more like a clustering model where the variance is no longer independent across individuals, and that's actually just going to exacerbate the problem even more. There's going to be an additional multiplier. Take, for example, the standard independent Poisson model where people walk in independently. A heterogeneous Poisson where there's some sort of clustering on if instead of it always being one unit that walks in the door, there's a group of unknown size with expectation greater than one walking through the door, that'll always blow up the variance. So if it turns out that the reason why your wife purchased the car was actually highly correlated with the fact that her friend had purchased that car, that's going to behave more like two cars being purchased due to whatever the root cause effect was. So I expect that actually to just make some of these problems a lot harder. But I certainly think that all of these sort of social network issues definitely matter, but they just make the problem it just sort of adds to the laundry list of complexity.
I'm not completely sure I would agree with your analysis that it would necessarily increase the variance. It certainly can. It may reduce the variance. It depends on the strengths of the effects.
Okay.
I think the bigger concern was it has. I think I'd rather not destroy the signel.
I would too. So
a bias which is significantly reducing the signal is a problem, right?
I agree. So if we reduce the signal, then we end up underestimating a lot of the ad effects.
Yeah, the variance you can potentially compensate just with more data, but at least you know, and you'd be able to observe the bias.
So just as an aside, in one study with one of the experiments we ran, we were able to get sort of Yahoo email and instant messenger data and be able to grab the social network. And we were able to sort of include a regressor, which was in treatment effect, interacted with like the number or share of friends that you have that you communicate with. The problem is that there's just so little information percolating across there. In some ways, that problem is actually quadratically more difficult than just the main effects, even in a clean experiment. And if these social effects are huge, then that would help a lot, and we'd be able to see the effects more. But as it is, those types of effects, in a lot of the research we've done so far, I've just had to add them to the list of like mismatched data, cash purchases, and other things where there's just a lot of things that can actually go wrong and can cause experimental estimates to be downward biased. But the difference between an experimental estimate where it's downward biased and overall estimates and observational estimates where the bias generally cannot be signed, that's a trade-off.
Sure.
So,
I understand, but I mean, the idea would be since you're randomizing, since you have the option to randomize, I was just suggesting maybe randomizing in a way that isn't sort of exacerbating.
Yeah, I totally agree. I think that's in some ways, I think that's an open research question, and we'll try to address that in the future. So thank you.
We're at 2:30. Why don't we thank Randall for a great talk?
All right, thank you.